Hello and welcome to the Maths Matrix. My name's Rebecca and in this video I want to do something a little bit different. I actually tried to film it over the bank holiday weekend because I thought it would be something really fun for me to do, but life just seemed to get in the way this weekend. One thing after another just went wrong every time I tried to film, so I'm having another go now and hopefully this one will be a little more successful. What I'm going to do is I'm going to be going through a really old exam paper from 1950. I think it'll be just something really enjoyable for me to do, but I'm hoping that there'll be some benefit for you as well in me doing that. Up to now, I've run the videos like lessons as if you were here with me. So we've made dictated notes, we've done worked examples, and we've done practice questions, all to improve your knowledge of a particular topic and hopefully boost your exam grade. That's fine, but I don't feel like it's given you a chance to get to know me yet, and I don't feel like it's given me a chance to show you how much I actually love maths. I like teaching, but I love actually doing maths as well. It makes me happy. I find it takes my mind off things. I just enjoy it, and I don't think that's had a chance really to shine through yet in the videos. Also, and this is really vain, but when I film the videos like that, I have to make sure that the board is the focal point because it's important that you can see what I'm writing, understand the working and copy it down. That's led to some really unflattering angles of me. I feel when I edit the videos that I've always got a slight double chin because I'm looking down slightly at the board and then I'm reaching across in front of it to write on it without blocking your view of it. And when I edit the videos, I'm just so aware of my big fat arm right at the front of the shot, and I just feel really kind of fat and ugly on the videos, and when I edit them I just keep thinking, oh no, what are people going to think? You look awful, you look a mess. And I know it shouldn't matter what people think. I know that the videos are maths videos and that the maths should be the focus, but I just feel a bit like you've never seen me looking decent and you've not got to see my proper personality up to now. I think I'm even more conscious of it because so much of YouTube seems to be devoted to looking nice. It seems like every other video on YouTube is a hair tutorial or a makeup tutorial or a lookbook, and the people in those videos always look really nice and they've got the cameras angled so that they look lovely and they've got nice lights, and it just seems to make the difference between their videos and my videos even more marked. I keep comparing myself to bloggers like Freddie My Love and Fashion Mumbler and Mrs. Midwest, and I just feel so inadequate by comparison because their videos are amazing. So I wanted to make a video where I wasn't standing in front of the board and where I could show myself at a slightly more flattering angle for a little while before we move over to the paper itself. I know that's very vain, but I am only human. People often ask me, are GCSEs getting easier? And I always say yes, I think that they are. That might not be the politically correct answer, it might not be the popular answer, but I think that GCSEs have got easier over the years. And I think that's partly why they were revamped a few years ago, because they'd got so easy that they almost weren't worth having. And I think it was important that they were made slightly more difficult again so that they became a qualification that actually meant something. I thought it would be fun to look at a really old past paper so that you can see whether you think they've got easier or not. So what I have here is an exam from 1950. They didn't have GCSEs in 1950. They were called O-levels then, but they were a similar thing. They were exams taken in year 11 when you left school. And this is a University of London matriculation examination from September 1950 in elementary mathematics, testing arithmetic, algebra and numerical trigonometry. So arithmetic, algebra, numerical trigonometry, you still get those on papers today. I thought it would be fun to have a look at it together, see if I can do it, see if you can do it, and see how much is still in common with what's on the syllabus today. I don't know if I'll be able to do it or not. I don't know how much of it you might be able to do. I've had a look through already because, as I say, this is not my first attempt at filming this video, so I haven't tried the whole thing, but I did have a glance through before I started filming just to make sure that it was worth doing at all, that there'd be anything at all that's familiar to modern GCSEs and A-levels. There are bits that are in common with modern GCSEs, so GCSE students, you will be able to do some of it, and A-level students, you'll be able to do more of it. In fact, there's quite a bit of it that A-level students should be able to do. I thought it might be useful for you to see how I react when I'm in a situation where the material might be unfamiliar to me and I don't actually know whether or not I can do the question, because that's the situation that you're going to be in your exams. Whether you're at GCSE or at A-level, it's highly unlikely that you're going to sit down on the day of your exam and know how to do every question. There will be material that's unfamiliar to you. There'll be things that are in a strange context, and there'll be questions where you start them and you don't know whether or not you're going to be able to finish them, and you don't know whether or not you've got the right answer. I find that students are often frightened to start questions when they don't know how to finish them. I find that people often don't want to start writing unless they're sure that what they're writing is correct. I find that especially at A-level actually. It's true at GCSE as well, particularly on the 5-mark questions or even 6 markers if you're on certain boards where they offer 6-mark questions. But at A-level, it's not uncommon to get questions that are worth 8 marks, 10 marks, even 12 marks, all in a single question. And I tell my A-level students off quite often because they'll look at something that's worth 8 or 12 marks and they'll just say, after a bit, after they've gazed at it for a while and done absolutely nothing, they'll say, I don't know. And I'll say, well, how can you? I don't know the answer in my head either. It just isn't possible to do it all in your head, get to an answer and then start writing. There's too much going on, and people are often scared to start because they don't know whether or not they'll be able to do it. I think it will be useful for you to see me start when I don't know if I'm going to be able to do it, because that is what you will have to do in your exam. And I want to give you the confidence, I suppose, to start even if you don't know if you're doing it right, because in bigger questions, the larger ones at GCSE and most of the questions at A-level, you have to start because that first line of working unlocks the next bit of the question, and then that bit of the question unlocks the next part, and in doing a little bit at a time, you soon find your way to the final answer, even if you didn't know that you could. So I just want to show you really my thought processes when I'm faced with unfamiliar things. Hopefully you'll get to see me make some mistakes, you'll get to see me think I don't know what to do, and actually this paper doesn't have a mark scheme with it, so I can't even use the mark scheme to kind of prompt me or help me or anything. I'm very excited to see how I get on, so let's get started. Right, this is the paper, and I'll try and remember to link it in the description below in case you want to download a copy for yourself. It's a University of London matriculation examination from September 1950 in elementary mathematics, arithmetic, algebra and numerical trigonometry. I presume ordinary paper just means O-level, whereas nowadays they have GCSE written on the front. And it was a 3-hour exam. Candidates must not attempt more than 9 questions, and that was out of a possible 10 questions. It doesn't say what happened if they only did 7 or 8. I don't know. It just said they couldn't attempt more than 9. So question number 1 is here. If you want to have a go, then just pause the screen there so that you can see what's going on and have a go at it, and then come back when you're ready. I'll read it out for those of you who aren't going to pause the screen. The charges for electricity in a household were 15s and a quarter. The S means shillings. And in addition, 3/4 D, that means 3/4 of a penny for each unit used. In 1 quarter, 808 units were used. here a quarter means a quarter of a year, so a 3-month period. I think quite a lot of utilities are still billed on a quarterly basis. If gas had been used, the quarterly charges would have been 2 shillings and 6pence for meter rent and 1 shilling and 2pence per therm consumed. Assuming 1 therm to be equivalent to 200 cubic feet, how many cubic feet of gas could have been consumed in the quarter if the total charges for gas had been the same as for electricity? Well, that's a mouthful of a question, isn't it? I am far too young to remember shillings and pence. They were well before I was born. But I think that there were 12 old pence in 1 shilling. People sometimes say that a shilling's the equivalent to 5p, but I think they mean 5 new pence. I don't think an old penny and a new penny were worth the same amount of money. So I think that there were 12 old pence in 1 shilling. So this was all before decimalisation, this paper. I'm just going to put this to the side now so I can actually write. So for electricity, there's a one-off charge of 15 shillings a quarter. That means every 3 months you've got to pay 15 shillings, even if you've not used any electricity. So that's like a flat rate fee. Then there's also a fee of 3/4 of a pence. I will put it as D. 3/4 of a pence for every unit used, and 808 units were used. So what we need to do is find 3/4 of 808, and that will give us the cost for the electricity that was actually used. So thinking back to fractions of quantities, if you've watched that video, 1/4 of 808 is 808 divided by 4. So 808 divided by 4 is 202. And we don't want 1/4, we want 3/4. So 3/4 of 808 is 606. So the cost of the electricity was 15 shillings plus 606 pence, okay? We now need to add those up, but at the moment they're in different units. What I'm going to do is I'm going to convert the shillings into pence so that I can add them together. I think I'll find it easier to do it that way. So 15 times 12 is what needs to happen now because there were 12 pence in a shilling, I think. 5 2s are 10. 2 1s are 2, and add that on makes 3. 0 there, 1 5 is 5, 1 1 is 1, and adding the 2 together makes 180. So that is equivalent to 180 pence. So the total cost of electric I would obviously do this neater if I was in a real exam. I'm having to try and make sure that you can see what's happening all in one place, so I can't be perhaps as neat as I'd like. But the total cost of electric is 180 pence for the charge itself, plus 606 for the electricity used, which equals... I'm sorry if I do some really basic calculations on paper that I should be able to do in my head. It's because I'm speaking at the same time. I find it very hard to talk and think at the same time. So if I do some really easy sums that I should know in my head, it's only because I'm talking to you as I'm doing them. So the total cost of electric was 786 pence. And I'm just going to leave it in pence for now, rather than convert it back to shillings and pence. The question then essentially tells us that the same amount of money is going to be spent on gas as we've spent on electricity. So we have that much to spend on gas, and we're being asked in a roundabout way, how much gas will that many pennies get you? So for gas, we have 786 pence to spend. The quarterly charges for gas would have been 2 shillings and sixpence for meter rent. That's like the one-off charge of 15 shillings there. So whether or not you use any gas, you've still got to pay your 2 shillings and sixpence per quarter just for renting the meter. So 2 shillings and sixpence. Feels weird writing that. I've never had to write shillings and pence before. Would be equivalent to, if there's 12 pence in a shilling, then 2 shillings would be 24 pence, and adding the 6 on would make 30 pence. So 2 shillings and sixpence equals 30 pence. So they had 786 pence to spend on gas, but 30 pence of that per quarter was for the meter itself. So 786 take away 30 gives us 756 pence left to spend on the gas itself. The gas itself cost 1 shilling and twopence per therm. So 1 shilling and 2 pence must be equal to 14 pence. And that's per therm. I've never heard of a therm. I don't know if therms still exist. We don't actually have gas at our house, so I don't really know what a gas bill would look like. I've never lived anywhere with gas. And we now need to know how many therms we can buy for 756 pence. So what we've now got to do is 756 divided by 14 to work out how many therms we can buy. I'm actually about to make a really stupid, very embarrassing mistake now that means I got the whole of the rest of this question wrong. I won't tell you what it is in case you want to spot it for yourself, but I was mortified when I was editing and I realised the silliest thing of all is that I did suspect as I was doing it that something wasn't quite right, and I checked it off to one side, and when I checked it, I got it wrong again. I think that sometimes happens in maths. You kind of become fixated on your first answer, and even though you think it doesn't feel quite right, when you check your calculation, you sometimes just make the same mistake again because that first answer is on your mind, and I think that's what happened there. I know why I made the mistake. It's because I was not concentrating. I was too focused on what I was saying to you rather than what I was doing, and I was trying to multitask. I was trying to do calculations and speak at the same time. I left the mistake in because it would have been hard work to try and refilm a section and edit it and put it right, but also it just seemed more honest to leave it there. I think it shows that you're never too good to make a stupid mistake and that you always need to be concentrating when you're doing maths. So when you're doing your maths, and particularly when you're doing mocks and exams, just try and take your time and concentrate on the questions, because it's so easy, however good you are, to do something really, really silly like that. You don't want to be throwing away marks on an exam. 14s into 7 doesn't go. 14s into 75 would be 14, 28, 42, 56, 60, 74. 1, 2, 3, 4, 5, 6. 6 remained a 1. And 14 into 16 goes once, with 2 leftovers. So we can afford to buy 61 therms. I'm not sure whether you can buy part of a I guess you can buy part of a therm. I mean, gas is like water, isn't it? It kind of flows. So you don't need to have either 1 therm or 2 therms. You could probably have 1.5 therms, but I don't know whether the gas company charges per part therm. So this remainder I'm just going to ignore. The modern day GCSE equivalent that I could think of would be, you know, those questions where you're off to buy tiles or polish or paint or something in a problem context question. you have to assume that the shop won't sell you half a can of paint. You have to assume that the shop won't sell you part of a box of tiles. So if you need more than 4 boxes of tiles to do your bathroom or your kitchen or whatever the question's on about, then you're forced to buy 5. I'm going to assume that the same thing works here. I'm going to assume that because we can't afford to have 62 therms, because we can only afford to have 61 and a bit therms, I'm going to just assume that they'd round it down to 61 and say, well, if you can't afford 62, then 61's what you're having, and therefore I'm going to ignore this remainder. Unfortunately, this paper doesn't come with a mark scheme, so I don't know if that's what actually happened on this exam or not, but that's what would happen in a modern day exam, so I'm going to go with that and say 61 therms. And then we're told a therm is equivalent to 200 cubic feet. How many cubic feet of gas could have been consumed? So now all we need to do is times 61 by 200. Well, 61 times 100 would be 6,100. So 61 times 200 must be twice that, which would be 12,200. So we could afford to buy 12,200 cubic feet of gas, which is what they actually asked in the first place in the question. Let's have a look at question 2. So again, I'll put it on screen if you want to hit pause and have a go at it yourself. It says a 440-yard running track consisted of 2 parallel straight parts, each 120 yards long, joined by semicircular ends. Find the radius of a semicircular end correct to the nearest foot. Take pi to be 3.142. That's because they didn't have a calculator in this paper. So nowadays, this kind of question will probably be on a calculator paper. It then said, if a man runs round the track in 52.3 seconds, find his average speed in miles per hour, correct to 3 significant figures. Right, let me just turn over so I've got some space. So what we've got here is a running track with 2 parallel parts, each 120 yards long, with semicircles on the ends. And we know that the overall perimeter is 440 yards. Yards were the old-fashioned equivalent of metres. A yard and a metre is almost the same unit of measurement, actually. They're not exactly the same, but they're pretty close. So yards, metres, roughly the same. The straight sides are each 120 yards. So what we've got is 440, take 120, take another 120. So take 240, gives us 200 yards left for around those edges. And since these are semicircles, they're both going to be the same size as each other. So you've got 100 yards there on that curly bit and 100 yards there on that curly bit. Okay? 2 semicircles being put together would make a circle. So what we've got is a circle whose circumference is 200 yards. And the question is asking us, what's the radius of that circle? So we're being asked to find the radius. The circumference of a circle is either pi d or 2 pi r. Most schools nowadays teach pi d, I think, but we learned it at school as 2 pi r. Obviously, the diameter is twice the radius, so those formulae, although they look different, are the same thing, really. And we're being asked, what is the radius of a circle? Even though we're being asked what the radius is, I'm going to work with this version and then just divide it by 2 at the end, because I think that this formula will be more familiar to most of you. So we've got 200 yards is equal to pi, which they're telling us is 3.142 times the diameter. So the diameter will be equal to 200 yards divided by 3.142. But they want the answer to the nearest foot. So what I'm going to do, because they want the answer to the nearest foot, I'm going to convert yards into feet. You don't need to know this, and you probably don't if you're quite young, but there's 3 feet in a yard. So like there's 100 centimetres in a metre, there's 3 feet in a yard. So that is equivalent to 600 feet. So I'm going to divide 600 feet by 3.142. And that will give me the diameter in feet. Now, they didn't have a calculator to do this, so what I'm going to do is I'm going to times that by 1,000 to give 600,000 and divide by 3,142. So 600,000 divided by 3,142 is the same as 600 divided by 3.142, except it's easier to work with because there are no decimals. You would then need to do an exceptionally long division, which I'm just going to do on a calculator to save time, because that is going to take up a lot of minutes of division. And I'm aware that this video will get really long if I do all the division longhand like that, because it was a 3-hour exam. Remember, this was a 3-hour exam, and I don't want to make a 3-hour YouTube video. I don't think anyone would watch it, and I can't imagine how long it would take to edit and upload and process. So for the interest of speed, I'm just going to do it on a calculator. And that produces an answer of, I don't know if you can see this bottom bit, but it produces an answer of 190.961172. So I'll just put ... to denote that. And that unit would be feet, because I converted those yards into feet. Now, it doesn't say it wants the answer back in yards and feet. It just says correct to the nearest foot. So to the nearest foot, hang on, I'll divide it by 2 first though, because that's my diameter. So if I now divide that answer by 2, that gives me 95.4805 stuff, ... In an exam, if you don't want to write the whole display down, it's fine to just write a few decimal places and then put ... I'm not using very many here because I'm not in a proper exam. Always in an exam, work with a higher degree of accuracy than the answer is required in. So if the answer is required to 3 significant figures, I would say work in at least 5 until the very final stage. But if you don't want to write your whole calculator display down every time, then it's fine to just write a few bits and then put ... You won't get marked down for that. So the radius is 95.480 other stuff, and they wanted it to the nearest foot. So to the nearest foot, that would be 95 feet. Okay? And what would have been hard really about that question in the old days when it was done without a calculator is the length of time it would do to do all that division without a calculator. You'd just have to be really careful, and it would be quite laborious, which is why their exam would have been so much longer than a modern day exam. The question itself up to this point is not vastly different from what you might get on a modern day GCSE. It's just that the units are different, and it would be on a calculator paper nowadays because calculators have a pi button. The next bit says that the man runs around the track in 52.3 seconds and says find his average speed. So this then is a speed equals distance over time scenario. So we have speed equals distance over time. And we know that the distance of the whole track, so he runs around the whole track, which is 440 yards. And he does it in 52.3 seconds. The problem now, though, is that because the distance is in yards and the time is in seconds, the speed that we get out of that will be in yards per second. And it didn't want the speed in yards per second. It wanted it in miles per hour. So the answer would have to be converted into miles per hour. Here I'm stuck because I don't know how many yards there are in a mile. And as it wants us to convert yards per second into miles per hour, we would need to know how many yards there are in a mile, and I don't. So at this point now, I am stuck. I feel like I ought to know how many yards there are in 1 mile. I feel like I've heard it on Tipping Point and The Chase. This is something I ought to know, but I don't know because we don't really use yards anymore. We use, well, I don't really know what we use. I use a bit of a hybrid, to be honest. I would measure a medium distance in meters, but I measure smaller distances in feet and inches. And I always think in terms of miles rather than kilometers. So I'm a bit of a hybrid child. I'm not quite fully metric and I'm not quite fully imperial either. But I don't know how many yards there are in a mile, even though perhaps I ought to. So I am now stuck on this question and cannot finish it. So the answer to whether or not a maths graduate can pass an O-level on this question might be no. It's worth mentioning though, because this is relevant to modern day GCSEs, that the units you put into a speed, distance, time question determine what units pop out. So if on a modern day GCSE they give you a distance in meters and a time in seconds, that means the speed you get out will be meters per second. If they wanted the final answer in kilometres per hour, you're going to have to think, well, if I do this many metres a second, how many metres would I do in a minute? How many metres would I do in an hour? And how many kilometres is that equivalent to? Okay, so what goes into a speed, distance, time question unit-wise determines what comes out. And if that's not what the question wanted the units to be, then you're going to have to change them. All right, so there is something to be gained from this question, even though I can't finish it. Moving on to question 3. I'll just pop it on screen there for if you want to have a go at it. So there are 2 factorised questions to do in part 1, and then part 2 is also a sort of factorising, but not something that you do at GCSE. So for 3A, move the paper again, we have to factorise p squared minus q squared minus 2qr minus r squared. You might notice I've just realised that I've got pink sleeves on the screen. It's a really chilly room where I do the filming, and by the time I'd finished faffing with the introduction, doing numerous attempts at that, I was really cold, so I went in and put a cardigan on. So that's why I'm now in pink sleeves when before I was in a dress. At GCSE we learn that there's 3 types of factorising: common, quadratic and the difference of 2 squares. This thing here that I'm being asked to factorise isn't really any of those. So I don't know if there's some other types of factorising that I don't know about. It's quite possible that there's some other types of factorising that I don't know. However, what I'm going to do is the first part of this is a difference of 2 squares. So the first 2 terms, p and q, satisfy a difference of two squares scenario, so I'm going to factorise those like that. The next bit I'm going to factorise separately using common factorising. So I'm going to pull r out as a common factor, negative r, and in brackets then I'm going to put 2q plus r. And I'm going to have that as my final answer. It's really annoying that there's no mark scheme because I can't check whether I'm right. And also, because it doesn't say how many marks the question was worth, I don't really have any indication as to how much work would have been involved in doing it. On a GCSE, you should always use the marks available to give you a hint as to how much work might be involved. So if you have a 1 mark question on a GCSE, the answer should be very easy to get to. If you're doing a 4 mark question on a GCSE and you think that the answer is very easy to get to and you don't have any lines of working or just 1 line of working, then you've done it wrong. The answer to a 4 mark question should require a few stages of working. But because I don't know how many marks this question was worth back in 1950, I have no idea really whether it was a straightforward 1 marker and this was the answer, or whether there was more to it than that and I just don't know about it. So unfortunately, I don't know whether I've got that one right or not. That is a factorised version, but I don't know whether it's the factorised version that they wanted. Likewise, in part B, we're being asked to factorise that. The only thing I know of to do with that is pull out 2 as a common factor, because each of those things divides by 2. So 2xy minus... I was wrong. You do not pull 2 out as a common factor because 15 does not divide by 2. So what I'm going to do instead is, again, I'm going to split this into 2 halves. I'm going to pull 3 out as a common factor there, 3x in fact. I'll pull 3x out as a common factor of those 2 terms and then put 2y minus 5 in brackets. And then I'm going to view this as a whole separate thing and put plus 2, open bracket, 2y minus 5. Again, I don't know if that is... Oh, actually, no, I do. But what I'm now going to do is I'm going to, because the 2y minus 5 part repeats, and you'll only know this if you know how to do harder quadratic factorising, but because the 2y minus 5 bit repeats, I'm going to bring these terms into a bracket of their own to give me 3x plus 2, 2y minus 5 as my final answer. Doing part B has just made me think of something for part A actually. I've just played about at one side. If I rewrite this as p squared minus q squared plus 2qr plus r squared, that bit there will factorise to q plus r, lots of q plus r, and I can put the p squared minus in front. So actually, that will more neatly factorise. The part A will more neatly factorise as p squared minus q plus r squared. So actually, I think that that would have been what they wanted in part A. So I think it would have been that rather than that. So ignore my first answer and we'll go with my second answer, which just shows that if doing a later part of a question makes you realise that you've got an earlier part wrong or gives you a good idea for something that you encountered earlier in the paper, that's absolutely fine. The examiner can't tell what order you've done things in, so if something does occur to you later, then feel free to go back and change it. There's no shame in not getting something right first time. I'm going to need to turn over for the second part of the question 3 because it's going to be quite a long one. I'll just bob it back on the screen. GCSE students, you will not be able to do part 2, although you will be able to follow some of the working. It's not something that you learn until A-level. A-level students, you should be able to do this because it is the factor theorem or the remainder theorem, whatever you want to call it. Okay, so GCSE students, just don't worry about this bit for now. A-level students, you ought to be able to do this because you know that the remainder will be F2. So the remainder will be F2. But because x minus 2 is a factor of the cubic function in question, there won't be a remainder. So we also know that the remainder is 0. So what we know, if we have, I'll just write it down here, then you can see it again. I can't have both bits on screen at the same time. That's the actual f of x itself. So if I sub 2 into that, then what I get is 2 cubed minus 4 lots of 2 squared plus c lots of 2 plus 6. And I know that F2, which is that, gives us the remainder, and that the remainder is 0 by the factor theorem. So I'm going to stick equals 0 on the end there. So what I now have is 8, 2 squared is 4 times 4 is 16, plus 2c plus 6 equals 0. 8 minus 16 is minus 8. Plus 6 is minus 2, so 2c minus 2 equals 0. So 2c equals 2, so c equals 1. So that's finding the value of c done. That's nothing for you to worry about at all, GCSE students. There's nothing there that you could have done yet. We now need to find the remaining factors of the expression itself, so of this. So we now know that f of x is x cubed minus 4x squared. We know that c is 1, so plus x plus 6. There's a couple of different ways that you can now do the rest of the question, which is to find the remaining factors. I'm going to use the way that I like, but if it's not the same method that you use, then that's absolutely fine, as long as we all get the same answers in the end. So A-level students, do whatever method you like to do this question, but you ought to be able to do it. And if you can't, then that means you need to revise this topic because it's something that's likely to come up on exams. The way I would do it, I hope you can still see what I'm writing. I would say x minus 2 lots of ax squared plus bx plus c equals x cubed minus 4x squared plus x plus 6. I would then expand these brackets to say ax cubed plus bx squared plus cx minus 2ax squared minus 2bx minus 2c equals x cubed minus 4x squared plus x plus 6. Okay? I would then equate coefficients. If you don't use this method, it is okay. You do use equating coefficients quite a bit at uni, so I think this is probably why I prefer this method, and it's always the method I teach. If you are planning on doing maths at uni, then I would get familiar with the equating coefficients method because it's something that you'll encounter again. There's 1x cubed on this side and there's one bit with an x cubed on this side, so it follows that a must equal 1 because we need there to be 1x cubed in order for those things to be equal. Regarding the x squareds, we've got b x squared minus 2a x squared, and over on that side we've got minus 4x squared, so it follows that b minus 2a must equal minus 4. But we know that a is 1 from the previous part, so b minus 2 equals minus 4, so b equals minus 2. I'm going to have to move across to this bit of paper. Doing the same for our x term, we have cx minus 2bx, and we know that that has to equal 1x. But we know that b is minus 2, so c minus 2 lots of minus 2 equals 1, so c plus 4 equals 1, so c equals minus 3. What that then means is that we have x minus 2 lots of x squared minus 2x minus 3. So that original cubic is equal to that. And I now, to find the remaining factors, need to factorise the quadratic. So x minus 2 is obviously one of the factors, but I need to factorise that quadratic to find both factors that are left. And I can do that by putting minus 3 in one bracket and positive 1 in the other bracket. GCSE students, you can factorise quadratics, so you should be able to factorise that part. And that would be the final answer. So those are the factors of the original cubic, and we found C earlier, so that question is done. Let's have a look at question 4. I'll pop it on screen so that you can hit pause and copy it down if you want to have a go yourself. Higher ability GCSE students, those of you going for levels 7, 8s, 9s, you should be able to do this question in its entirety without any prompting. A-level students, you should be able to do this question in its entirety without any prompting. If you're a sort of level 5, 6, you probably won't be able to do part A without some clues, but you should be able to follow the working and do bits of it. It will become familiar to you what it is. The part B, perhaps not so much, but there's definitely things you can learn from watching it be done. So don't worry if you can't follow the whole thing, particularly not because I know I haven't put any algebra videos up yet, but if your algebra is quite strong, then most of you should be able to do at least some of this question. So let's get started. So for A, we're told that 2x minus 3 over y equals 0, and also that x plus 1 over y equals 5. These are just simultaneous equations. They're just presented in a way that doesn't look quite as pleasant as how they might be given to you nowadays on a GCSE paper. But linear simultaneous equations is what they are. So these do still come up at GCSE, and A-level students, you should be able to do them with no prompting whatsoever. What I'm going to do is I'm going to rearrange this to make x the subject. So if I subtract 1 over y, then that'll leave me with just x. So I'm going to subtract 1 over y from both sides of that equation to give me x equals 5 take 1 over y. I'm then going to put that chunk in place of x there. So I'm going to substitute 5 minus 1 over y in place of x in this equation. So that's going to give me 2 lots of 5 minus 1 over y minus 3 over y equals 0. I'll just put a line there so we don't get confused by that bit. So all I've done is picked up that chunk and written it where there was an x. I'm going to expand those brackets, so 10 minus 2 over y minus 3 over y equals 0. And then rather than try and take those away from each other as they are, I'm just going to get rid of the fractions by multiplying out by y to give me 10y minus 2 minus 3 equals 0, to give me 10y minus 5 equals 0, to give me 10y equals 5, so that y equals 5 over 10, which is equivalent to a half. So we have y equals a half, or 0.5. That's our first solution. We then need to work out what x is. So x equals 5 minus 1 over y, which equals 5 minus 1 over a half. What did I say in the fractions videos, GCSE people? I said it's important that you know how to divide with fractions because it will be tested somewhere on an exam, and if it's not tested explicitly, where they just say here are some fractions, divide them, they'll test it somewhere like this. We now have to do 1 divided by a half. So 1 divided by a half is the same as 1 times 2 over 1, which is the same as 2 over 1, which is the same as 2. So the answer to that bit there is 2, and 5 take away 2 is what that becomes, so that x equals 3. So the overall answer to this question, which I'm scruffily just going to write here so that I don't waste too much paper, is x equals 3, y equals a half. And that's the final answer for that one, okay? And you might still get something like that nowadays. It would be unusually difficult if they presented it to you with fractions like that, but it's not impossible that they could do so, and linear simultaneous equations are still very much on the syllabus. Part B is also still very much on the syllabus. So there's nothing particularly different about this olden days algebra and modern algebra. A-level students, you should be able to do that as it is with no prompting whatsoever. I just realised I've written the whole thing without it actually being on the screen, sorry. A-level students, you should be able to do that absolutely as it is. If you can't, then you need to go and have a look at some back-end GCSE past papers and tighten up your GCSE algebra a bit, or else it will cost you in your A-level exams. GCSE students who are going for one of the higher levels, this is a good way that you can get marks towards the back of GCSE papers. They're called algebraic fractions. That's what it would be. The only slight difference is that probably it would be presented to you nowadays like this. So normally they just give you the fractions on the left and the answer on the right, but all that's happened for me to get from there to there is that I've subtracted 1 from each side. So if it was given to you like that, that would be your starter step as well. There's then 2 ways that this question can be done. You can either think before 2 fractions can be added or subtracted, they must be expressed over a common denominator. So the way some people like to do these questions is they like to write these 2 fractions as one big fraction expressed over a common denominator. That's one way it can be done. The way I like to do it, and the way I like to teach other people to do it, is to just times out by one denominator at a time to undo the fractions altogether. But neither way is better than the other. The only reason that I tend to teach times out by one denominator at a time is because it's something that's accessible to everybody, and you don't need quite as good of an understanding of algebra and fractions to be able to do it. So it's possible to teach people to do these types of questions if they know to times out by one denominator at a time without their maths being quite as strong, which is obviously a good way to boost their exam result. But both ways work. Everybody will get the same answer in the end. So I'm going to times out by x plus 2 across the board first of all. If you prefer to do it the other way, then feel free. 3 plus 4 open bracket x plus 2 over x minus 3 equals minus 1 open bracket x plus 2. When times in chunks of algebra, we use brackets to denote this. That's what I say to students in their dictated notes. And when I do algebra with you on videos, that's what I'll be saying to you in your dictated notes as well. We still have a denominator, so I'm going to times out by that as well, so that I'm undoing that fraction as well. So that'll give me 3 lots of x minus 3 plus 4 lots of x plus 2 equals minus 1 x plus 2 x minus 3. A-level students, well, any students, you don't have to write in these bits and bobs, but when you're learning, it can be helpful to keep track of what's going on. I'm going to expand the brackets. 3x minus 9 plus 4x plus 8 equals minus 1 lots of x squared minus 3x plus 2x minus 6. Don't worry if you can't expand your brackets so quickly. I certainly couldn't when I was doing my GCSEs or even A-levels. So if you need to do parrot beak or foil off to one side, then do. I'm just trying to save paper so that I can fit it all on one page for you. Gathering like terms, 7x minus 1 equals minus 1 x squared minus x minus 6. I then can times everything by that minus 1 to give minus x squared plus x plus 6 on the right, and nothing's changed on the left. That's starting to look a lot like a quadratic equation, but before quadratic equations can actually be solved, they have to be equal to 0, and mine's not equal to 0. Also, I'd prefer to work with a positive number of x squared, so I'm first of all going to move the x squared over there to give x squared plus 7x minus 1 equals x plus 6. I'm then going to subtract x to give x squared plus 6x minus 1 equals 6, and I'm then going to subtract that 6 to give x squared plus 6x minus 7 equals 0. We now have a quadratic equation that is equal to 0, so we can go ahead and solve it by factorising, completing the square or the quadratic formula. This will factorise to plus 7 minus 1, which gives me the two solutions. I'm running out of space. X equals minus 7 is one solution, or x equals 1 is the other solution. Okay, so that is still very typical of what might be on a modern day GCSE, or sometimes even A-level maybe. So nothing's changed there. We can do that. Question 5 then said, use your tables to find the cube root of 0.0276 and to evaluate that thing there. It doesn't mean use your times tables. That's not what it means by tables. Remember that this was a non-calculator paper because in 1950 everyone didn't just have a calculator. And on the front cover it said table of logarithms are provided. This question 5 was about using those table of logarithms to find answers to those questions. You would never get a question like this on a modern day GCSE because we have calculators now. We don't need to be able to find cube roots using table of logarithms anymore because we have calculators that can do it for us. And it's not a question that I can actually do because I don't have a table of logarithms. I have never used a table of logarithms. You don't actually learn about logarithms at GCSE, so again, logarithms aren't something that you need to worry about. What a table of logarithms actually was, it was like a booklet of answers to square roots and cubed roots and fourth roots of things, so that you could just look up from a list what the answer to a question might be. Except that sometimes they couldn't obviously print a booklet of every maths question in the world that you might ever need a calculator for. So sometimes little bits and bobs of manipulation would have to happen before you could look it up in your log tables. The only analogy I can think of nowadays is A-level students, if you're doing stats, when you have to look up in your stats tables things to do with normal distributions. Sometimes you've got to do a little bit of manipulation with your numbers first and then look something up in your tables afterwards. I can't do this question because I don't have a table of logarithms and I've never used them before. So question 5, I will have to miss out. I'm actually going to have to stop this video here because I've already been recording for well over an hour and I did my introduction in a separate video, so that's going to make several more minutes of footage, and I don't want the video to get too long because I don't think anyone's going to be sufficiently interested to watch it for hours and hours anyway. I would actually like to look at the rest of the paper though, because I would find it fun for myself. Like I said, I really love doing maths, so I think it would be something I'd enjoy doing. And I think the back end of the paper might have some stuff on that's still useful as well. I've not looked at it in too much detail, but I've certainly seen bits that are still in common with modern A-levels, though whether or not they're harder, I can't say at a glance. And I think there's some GCSE content on here as well, so it might be fun to look at the second half of the paper and upload that at some point. Even if I don't upload it, I'll certainly be looking at the second half of the paper for my own enjoyment. But if you would like a part 2 where I do the rest of the paper and we find out definitively whether or not the paper was easier or harder than a modern day GCSE, and we find out definitively whether or not I could do it, then please comment below and say yes, we want to see part 2 please. If you think it was really boring, this video, and you never want to see me work on a vintage paper again, then you can let me know that as well, but please be kind. I have a paper from 1940, I have some from I think 1968, and I also have some early GCSEs. I think they were first sat in 1988, but I have a set of GCSEs from 1988 to the early 90s. So if you would be interested in watching me do any more old papers, if it's something that you'd find useful or just entertaining, then do let me know and I'll do them from time to time. It'll make a nice change from doing proper lessons on the board. Thank you for watching. Please consider liking or subscribing, and I will see you in the next video where we will be probably doing percentages.